So our first panel is advances in deep neural networks. Neural networks can be trained with relatively modest amounts of information and then applied to large quantities of unstructured data. This panel will discuss the current state of neural networks and what changes they may bring as they continue to develop. Our moderator is one of the true pioneers in the area of artificial intelligence. Please welcome 2011 Turing Laureate Judea and his panel.
Welcome to the panel on advances in deep neural networks. And what we're going to do is start by introducing the members of the panel. Please come to the podium and introduce yourself and your relationship to this particular, in any order.
Hi, my name is Fei Fei Li. I'm a professor at Stanford University, director of the Stanford AI Lab, and I'm currently also chief scientist of AI and machine learning at Google Cloud.
I think we'll do it from the seats instead of standing up, so because we have mics on. My name is Stuart Russell. I'm a professor of computer science at UC Berkeley, and I work on pretty much all areas of AI except for deep learning.
Hello everyone, my name is Ilya Sutskever. I am the co-founder and research director of OpenAI. Previously I used to work at Google Brain, and I was a PhD student of Jeff Hinton. And I work on all areas of deep learning and on no areas outside of deep learning.
So my name is Raquel Hurtas, and I'm a professor at University of Toronto. I'm also a co-founder of the Vector Institute for AI in Toronto, and recently also the head of UberETG Toronto. And I work, I guess, in self-driving cars, machine learning, computer vision, and using deep learning.
Michael Jordan, University of California, Berkeley. Been doing machine learning for about 30 years. I'm interested in all areas of it, including deep learning, but not only.
We're going to give each panel member 7.5 minutes to make a statement about his or her perception of where the field is going. And I will start that with my own 7.5 minutes. When we finish the 7.5 minutes, we are going to interact informally among ourselves, reacting to each other's statements. And then we're going to open it for question and answers from the audience. So let me start my talk by mentioning that, like Stuart Russell, I too am foreigner to this field. And I have, of course, I was motivated by neural networks in the 1976 paper by Rumelhart, which got me to think about belief propagation in Bayesian network. But I left this field quite early, and I spent my time admiring the advances of this field from the outside, from an outside viewpoint. And this is what I'm going to present here today, an outsider perception of where the field is going. Well, I left this field partly because I realized that human beings are not good in handling information. human beings are very bad in processing statistical information, in obtaining statistical intuition. And the mode at which human beings are working is the causal mode, which means people are very good and very efficient in drawing causal conclusions from causal inputs, not so good in drawing statistical conclusion from statistical input. And what I'm looking at the field of neural network, I find, and the deep learning and the entire machine learning area, I find that it's primarily working in a statistical mode. Namely, the program improves its performance by optimizing parameters based on a stream of observational data. And that is something which we learned in our field of causal inference. We learned to avoid, and we learned to look down upon. We learned to avoid not us. I mean, it's already recognized by early statisticians that correlation is not causation. Moreover, we have a very good existence proof, and which happened 40,000 years ago, when our forefathers, Homo sapiens, took over the planet, over the Neanderthal and the Homo erectus species of human being, by virtue of one computational advantage they had. And this is to build a model of one's environment. This is all speculation, of course, but the question is, something happened in about 40,000 years ago, which anthropologists and historians find very hard to explain, and I think that we, computer science, can explain. And what happened there is that about 40,000 years ago, we find the first figurines or artifacts which depict worlds that could not exist. For instance, a combination of a lion head with a human body. The ability to imagine things that do not exist physically. That can only happen if the organism we are talking about has a representation of the environment and is able to manipulate that in representation internally by imagination before it is manipulated in the physical world. And that is one explanation of the reasons that there was an accelerated process over normal evolution. See? Snakes and eagles have developed over a million years. They've developed superb optical system that could not surpass by anything you can do in the laboratory. But that took a long survival of the fittest kind of evolutionary process over millions of years, and they end up with a very specific, perfect, superb system. They could not build eyeglasses or telescopes. That's something that human beings managed to do in only 1,000 years, which is, for us, computer scientists, raises a basic question: what computational facilities these people have in the cognitive evolution era that previous species did not have? And the hypothesis, which I find very satisfying, is that they had the ability to represent the environment and manipulate the environment and actually developed a market for promises. Because if you have this ability to predict the future on the basis of manipulating and build alternative worlds, then you can trade with promises. And you establish large communities on the basis of promises and so on. Coming now down to machine learning, we find that you can do very little with correlations, with statistical learning. And this is, and we have also found that theoretical classification which is organized in a hierarchy. On the first level, you have statistical reasoning, which can tell you only what is the likelihood that something else happens, given that you saw another variable or another proposition. What is the likelihood that, what can symptom tell you about a disease? Or what is the result of the survey can tell you about the election? And then you have a second level, which is totally divorced from the first one, which requires a substantial crossover. I call it theoretical impediment, and this is action. What will happen if I act? What if we raise prices? What if you make me laugh? And so on. That is the second level of the hierarchy. And the third level of the hierarchy is counterfactual. This is the language used by scientists. What if I would do things differently? Was it the aspirin that cured my headache or the television program that I watch? That the counterfactual is the top level in scientific level. So now, as we look at the working and the success of machine learning, we ask ourselves, are they aware of the basic mathematical limitation that were discovered in the causal inference era? Are we preparing a way to circumvent the theoretical impediment that prevents us from going from one level of the ladder to another level? I will end it by saying that data science should be a two-body problem. It's a relationship between reality and data. It's not a single body problem as we can see it practiced today. Data is non-science. Data in itself is not data science. Thank you.
So I have made some notes on the way over on Uber this morning. One of the great achievements of computer science in the last 50 years is that we can't think without a piece of metal in our hands. So I want to pick up on Yudah's reference of David Rumelhart. David Rumelhart was the inventor of the modern backpropagation in deep neural network idea in the early 80s. He died young from a brain disease. We all miss him. He would, I think, be in this room and probably over in this little section right here. And I remember I was sitting next to him in the 1980s when he was developing these ideas, and he had Minsky and Pappert's book in his hand, and he kept adjusting the program and running over and trying yet another problem out of him. And he says, yeah, I can do that, and I can do that, and I can do that. I kept asking, well, what can't you do? Because that's often the most interesting thing. And so we had some debate about that, and that's going to return in my conversation today. First of all, I don't think machine learning is best thought of as part of AI. I think it's best thought of as part of computer science. So all of our infrastructure, all of our systems should be intelligent, adaptive, and learning. And I think it's been actually a mistake to couch it too much in terms of AI. AI tends to think about how do we make a human, how do we do vision, speech, et cetera, et cetera. But if you think about all of our transportation networks, our logistic chains, our financial system, our healthcare, that's all intelligence and it's all computer science and it all has to use data. So that's the kind of thing we should be targeting. So if you think that way, there really can't be kind of one architecture of AI, and one architecture of machine learning, at least not yet. Maybe eventually it'll come out. You can't imagine layers of matrices trained by stochastic gradient descent as the architecture of all intelligence. That's farcical. So some of the debates are, well, neural nets can't do this or they can do this. If they can't do this, we have to cast them aside. There must be something else. Maybe it's Bayesian networks or maybe it's SOAR or something like that. And the AI literature has often been full of this fight between what's the architecture. All right, I don't think that's the right way to think. It's a toolbox, and neural nets will be forever in that toolbox. All right? But there are many other parts of that toolbox. And you have to think about the whole toolbox when you build a system like a self-driving car. It's not just a neural net. It's all the engineering around it. And our field is really just emerging by trying to provide all the structure around it and eventually lead towards an architecture, an operating system. It won't be just a neural net. So let's think a little bit about kind of what you can't do very easily with neural nets. You can do pattern recognition. You can do it at large scale. That's kind of somehow sort of surprising. When you start getting into areas of natural language processing, there I think there's been a bit too much hype. And in fact, I think even David Rumelhart would agree, there's been way too much hype about that. So natural language processing, when you start to cross over from syntax to the real world, to semantics, to something that's not just interesting, but true, that's a barrier we're still not very good at going past. So I was just in China the other day, and there was so much talk about neural nets and deep learning, and it's really, way too much hype. In particular, people were talking about chatbots. How good are the chatbots now? That every teenage kid is using the chatbots, right? So I looked at it a little bit. Of course, I can't speak Chinese, but it's just ridiculous. So these are systems that are kind of like the cheap, keyword-based or regular expression-based things of the past. They kind of see what you're saying and they throw something interesting sounding back at you, and they keep doing that for a while. When they get confused, because you use a word like he or she, and they have no clue what he or she means back in the past, co-reference, they'll just say something else interesting sounding and go off and talk about some other celebrity's news or something. And that works perfectly well for about 2 weeks, and then they get tired of it because the chatbot hasn't learned anything about them, the context, and the chatbot can't say anything true about the real world. It's just syntax, all right? So when you try to get past that and get it something true, you have to do things like, what's the metric? It's not just that people listen to it for a long time and it amuses people. The metric is, can we help people to do things? Do you get task completion? So if I put a chatbot inside of a program to make me to do travel arrangements for me, do I actually get the actual ticket in my hands? And there, it's very, very poor, right? And a lot of the problem has to do with natural language. Natural language is extremely hard. There's co-reference, there's anaphora, there's subtleties, there's metaphor, and we use it so fluently, and it's not just a matter of mimicking natural language. So translation is being done pretty well nowadays by kind of neural net type architectures. All right, but the error rates are still high enough that every sentence, which is about 25 words long, will have an error in it. All right, and getting that last part to be good enough that we really, that's strikingly, Turing would agree that we've solved the problem. We're very, very far from that. All right, we're very, very far from that. We don't understand the underlying semantics of what the language is referring to. We're just mapping strings to strings. That can't be the way that intelligence really arises. Okay, that's not what translation is. Now, if you go beyond translation to dialogue, all right, you're not going to have enough training data for dialogue. If I even think about the travel domain, all the things, like I say, I want to go to Paris, but not through Chicago, because I know there's always trouble. Oh, I might want to stop over in New York. Oh, no, let's not do that. Let's back up and do something else. All the paths that we could go down just in my conversation, do that over 1 billion people, we're not going to get enough training data for that. Okay? So just plain old neural net is not going to do that in 10 years. In narrow domains that are useful, and maybe you can build a company around them, yeah. All right? So that's kind of what's changed now, is some of these domains where we're faking intelligence with neural nets, right? We're faking it well enough that you can build a company around it. So that's interesting, but it's somehow not intellectually satisfying. Okay? Okay, so how can you say things that are true, right? That's hard. That's hard. And how do we get the flexibility of natural language? So let me invent a word right now. I'm going to invent the word grebe. Okay, never been used in English before, perhaps. All right, I'm going to say one sentence. All right, the grebe walked from SFO to the Westin in 30 minutes. All right, sorry. Computer scientists always know these little factoids that ruin your... Forget what you just said. All right, so I gave you one sentence. And now you know an enormous amount about grebes. I could ask you other questions about grebes, and you could answer them. And you could have uncertainty about your answers as well. All right? That's not what neural nets do. Neural nets require billions of training examples and going again and again through the training set. So something's missing. Something is missing. Okay? So we're in an era of enormous hype about deep learning, and yes, they can do great things, and yes, we can build some companies around them, and yes, it'll change the economy. But we're not there yet. Okay, so I would argue that deep learning is deep architecturally. There's layers, right? But somehow it's not deep in terms of abstraction and semantics. So semantics is where things are true. You don't need logic to talk about that. You just need a world. You need to talk about what's true. And abstraction is so important. The grebe example is kind of I just gave you a new concept. And what we're very good at is looking at something and abstracting, and that's what a lot of computer science is about. And neural nets don't do that very well. So there are layers, and somehow in some implicit sense, as you get near the end of all those layers, it becomes a little more abstract. But that's way too implicit for a science of computing. So I finished with 5 seconds left. That's pretty good, huh?
Thank you, Judea, and the organizers for this panel. I didn't know it would get this exciting since the start. So I have to say, Mike, I agree with everything you said. I grew up reading your papers as a student of machine learning. There's one thing I do disagree, is that I do think that machine learning is part of AI, and AI is a discipline for understanding intelligence and making intelligent machines. Just like physics has a whole set of tools from calculus to statistical mechanics, the set of tools for machine learning is the methodology we use for solving AI problems. But I agree with everything else you said. So I think, you know, undoubtedly we're living in one of the most excited, and using Mike's word, hyped era of AI, and mostly because of the recent renaissance and revolution of deep learning. And I want to begin my conversation with paraphrasing a quote from Churchill, and also inspired by another great mentor of my own, our colleagues, Jitendra Malik, saying that it's not the beginning, it's not the end, it's perhaps not the beginning of the end, it's probably the end of the beginning. And that's what I think where we are in terms of AI as a field, especially propelled recently by the advances of deep learning and machine learning. We're really entering a new phase, but there is a long way to go. And just a little bit of historical context, really thank you, Barbara, for paying tribute to the founding fathers of AI just 20 minutes ago. AI is a really young field with a very, very audacious goal. The audacious goal is as big, I think, as physics, which is probably a field to understand the workings of our nature and universe. AI is the field to understand the working of intelligence and develop machine intelligence. And I see the past 60 years of AI as what we call AI in vitro. AI was born in the laboratories. It was, the questions were asked. Our founding fathers started exploring a set of tools, a set of problems, and even just trying to understand how to measure AI, what are the metrics. But after these 60 years, especially in the recent past 5 to 10 years, AI did, as a field, did reach an inflection point, mostly driven by the great advances of machine learning, neural network being part of it, an important part, but not only neural network. I mean, a lot of you have worked on graphical models, kernel methods, optimization, support vector machines, and so on. So the combination of advances of computer science, especially in the hardware area, the combination of algorithms, especially machine learning as the language of AI, and then the emergence of data, internet, and brought us massive amount of data, gave us today's AI, where we're doing tremendously exciting things with statistical-based smart data analytics. And I do think this is a milestone of AI. It's not the solving all the problems of AI. So we've entered a new phase, what I would call AI in vivo, is that AI, for the first time, companies are founded by the advances of AI and using AI to solve a lot of the world's problem. Especially, many of us have heard humanity has entered the 4th industrial revolution. And here, while I'm on sabbatical at Google Cloud, I see every single industry being impacted by the massive amount of data and capability of data analytics. I see it in healthcare, in transportation, in manufacturing, financial services, in media and entertainment, in retail and commerce, just every single industry. And I think this is a very exciting time of AI. And also, AI is helping advancing science and other disciplines of science, be it medicine, be it material science, be it neuroscience, and very quickly social sciences, economics. So I do think this is a new phase of AI. And in the remaining 2 minutes, I do want to agree with Judea and Mike that there's a lot of more work to be done in AI. This kind of euphoria of AI has taken over and we've solved most of the problem is not true. I work in, for the past almost 2 decades, I work in computer vision and machine learning, and one of our work is ImageNet. A lot of you might have heard of it. It contributed to the advance of deep learning and object recognition. While we talk about celebrate the success, we hardly talk about the failures of ImageNet. And I look at ImageNet and we analyze all the success story, the leaderboards of ImageNet. We see a lot of failures. It boils down to the lack of ability to abstract and reason. So in ImageNet object recognition, while we can tag photos of dogs and baby faces and beach and food very well because there are data and of course cats, we cannot see small objects. We cannot find textureless objects. It boils down to the word that, where's my key? We have not even solved that problem because there's a lot of questions that are challenges that are remaining. That's long tail, that's lack of data, that's reasoning. And finally, I want to touch on that. I think the future of pushing AI forward has a lot to do with cognition. Just to quote another one of my favorite computer scientists, my colleague and also my next door neighbor, Terry Winograd, in his famous paper, Thinking Machines, which everybody should read, he says, the definition of today's AI is an algorithm that can make a perfect chess move while the room is on fire. So we can change the word chess to go, but still, it's the lack of contextual reasoning, lack of cognitive awareness of our environment, lack of the integrated understanding and learning that is still lacking. And I'm 25 seconds over, Judea is telling me. That's all I want to say. It's the end of the beginning. We're entering a new phase of AI. Thank you.
So I think Michael and Feifei have said a lot of what I was going to say about deep learning. I did want to mention, since we are here to celebrate Alan Turing in some sense. So Alan Turing, in many ways, was the father of AI even before Minsky and McCarthy and so on. So he was writing about it and talking about it in the late 40s and early 50s. And in some sense, not just AI, but the whole of computer science sprang from one idea that he had, that there's this mathematical object which is more powerful than any other mathematical object, than algebraic expressions, than derivatives, than sets, which is the program. And as Barbara pointed out, the mathematical community simply did not recognize these things as mathematical objects. And to some extent, you can't blame them. When you look at a COBOL program, it's hard to imagine that that is a mathematical object, but it really is. And that mathematical object has had a slow motion explosion that has ripped apart and reshaped our society, our economy. It's starting to do that. Universities are very slow, but it's starting to rip apart and reshape our universities as well. And AI is just one facet of the revolution that has come about because of that invention. So Alan Turing predicted that AI would make progress. His timeline was perhaps a little bit off, but not that much. The title of this panel on deep learning represents one breakthrough. So we might criticize deep learning, but I think it does represent a breakthrough of sorts that's happened in our ability to learn complex high-dimensional mappings. And that, in some sense, fulfills the early promise of neural networks from the mid to late 80s, when the AI community was somewhat skeptical, but we thought, well, perhaps the neural network guys will get perception, right? They'll get the low-level perception, the image recognition, speech recognition. They'll get that right, and then we'll be able to interface our symbolic reasoning systems to real-world inputs using neural networks as the pass-through mechanism. And to some extent, that's coming true now. And we're still trying to understand why it is that deep learning systems are successful. And there are the beginnings of some theoretical progress on understanding why they work, but I would say there's also still a huge amount of what people call graduate student descent, where you just spend graduate students making small changes to the architecture and the training algorithm and the parameters and the knobs to try to get better performance. And that's a disappointing form of cookery that I hope we'll get through that phase pretty soon. So I do worry that there's an overemphasis on big data and deep learning will solve all of our problems. And you could look back to the 1960s, the early stages of AI, where people showed that, with, for example, the general purpose problem solver that Alan Newell and Herb Simon developed, the GPS, they could solve problems, with solutions of length 5 or length 6, and then they thought, okay, well, that's it, right? It's just a matter of scaling up. And they neglected this little problem of exponential computation. And I think the deep learning community is neglecting this little problem of exponential data. And as Michael pointed out, there are lots of problems where the amount of data you would need to train a tabula rasa feed-forward network to solve a particular class of problems would be, 10 to the 75, 10 to the 5 million. The amount of data would dwarf the size of the universe. And we're never going to get that much data. There are many things that deep learning lacks. So deep learning systems are tunable circuits, and circuits lack the expressive power that we have in programming languages in first-order logic, the Turing equivalent kind of expressive power. They lack the compositional declarative semantics that make database systems and logic programming and knowledge-based systems useful. And they lack the prior knowledge. So when humans learn, for example, when humans are examining the output of the Large Hadron Collider, which is 50 terabytes per second, and discovering the Higgs boson in that data, they're not approaching that as tabula rasa machine learning systems. The guy who cleans up the floors in the CERN lab does not understand all the data coming out of the Large Hadron Collider because he doesn't know enough physics. If you didn't know any physics, you could not possibly understand the data coming out of the Large Hadron Collider. And a deep learning system will never discover the Higgs boson from the raw data itself just being fed in. So I think there's a growing understanding of this. I don't think the deep learning people are naive. Perhaps Ilya will contradict me. I think there's an understanding that we need somehow to combine these elements, the declarative semantics, prior knowledge, the capability for inference, with this really remarkable ability to learn these high-dimensional mappings from data. And I think there are many angles from which one could attack this problem. It might be that by taking deep learning architectures and gradually adding more structure and figuring out how they contain declarative information and combine it, that might be one direction. There's another field which has been going on a little bit under the radar called probabilistic programming, which takes the ideas that Judea had about compositional probabilistic models and combines that with the idea that Turing had about Turing machines, and lets you write probability models in an extremely expressive formal language. And that does have, in some forms, declarative semantics, compositional semantics, and does do inference. And in fact, these two fields are not that different. When you run a probabilistic program, although we typically show the probabilistic programming as, here are 10 lines that do tracking of objects in real time in video. There's the 10-line program. But when that 10-line program is running, it's generating what we think of as a deep generative network with tens of millions of variables, but also the structure of that network as the computation runs and as data arrives, the structure of that network is changing. It's continually adapting to the data, exploring different structural hypotheses. So in some sense, it's like deep learning, except much, much, much more capable and flexible. So it may be that coming from that angle and adding in some of the deep learning mapping capabilities, we will get some progress there. So I think there's a lot to do in AI. And Alan Turing predicted that eventually we would achieve and exceed human-level AI, and then he said, well, that's pretty much the end of the human race. If we're lucky, we'll be able to switch them off, but probably not. And so I think we have at least half a dozen major breakthroughs to go before we get close to human-level AI. But there are very many very brilliant people working on it, and I'm pretty sure that those breakthroughs are going to happen. So I'm devoting my life these days to figuring out what to do about that and how to make sure that things go well in the future. Thank you. Yeah.
Okay, so now this would be a good point for me to go. And I want to tell you why I like deep learning, why I find the field to be very philosophically satisfying, and try to explain, give some not very widely known explanations for why it works as well as it does. So the thing about deep learning that makes it work well is that the hypothesis class. So in machine learning, when you want to learn something, you need to make some non-obvious prior assumptions about what your function should be. The prior assumption we make with deep learning is that you have a circuit. And circuits are a pretty good object to learn. So if you have a really deep circuit, it can do a lot of complicated computation. I think it is not a well-known fact that a modestly sized neural network that only has 2 hidden layers can sort n-bit numbers. So the hypothesis class is very powerful without requiring a lot of parameters at the same time. So the really amazing fact about deep learning, which is powering all the advances that we see, is that we can actually find those circuits automatically from data with gradient descent. It violates all theory. It exceeds gradient descent on these circuits exceeded all expectations. And it's an empirical fact, and it's really amazing. There is one other thing about deep learning which is interesting, where there is an argument by which we could have predicted that deep learning would have succeeded at least for perception. And the argument goes like this. If you look at, if you do a bit of introspection and we look at our vision and we look at our speech, you notice that we can see and we can hear things really fast. So you look at something in a fraction of a second, you know what that is. But our neurons are so slow, they fire at most 100 times per second and usually much less. Well, this suggests that the process of vision and speech and some expert perception, if you ask experts, experts often know what to do in complicated situations right away. This is a massively parallel process that doesn't require many steps. So kind of like a deep neural network, a very large deep neural network. And so, well, then what the question becomes, can we take the biggest neural network that we can? Can we get the biggest computer we can and train the biggest neural network that we can and see how well it's going to do? And it turns out that this works well enough to be useful for a lot of tasks. The other thing which is interesting about deep learning is that these models are so hard to understand. I think vision is a good example. I can speak for myself. When I was thinking, what kind of computer program could possibly solve vision? It was just an incomprehensible program. What kind of code, what kind of computer code could possibly do that? Well, if you assume that these perception problems are truly difficult to comprehend, and you notice that neural networks are truly difficult to comprehend, then it's actually pretty good. Because it's like fight fire with fire. It means that you found an incomprehensible solution to an incomprehensible problem. And I think we can make good analogies to evolution with natural selection. Just like with learning, we have a pretty good understanding of the process of learning. We can make certain statements about what the result will be. As we can with natural selection, biological evolution, we can predict that you'll have certain organisms, they'll be reproducing with high probability, they'll have, certain statements can be made, even though it's very hard to understand how biological organisms work. So I think this is a similar thing we're seeing here. And then there is a last thing which I want to highlight, which is really important, and that's compute. Compute has been the oxygen of deep learning. And if you think about it, it makes perfect sense. Let's go back to the early 90s when people are excited about neural nets and they say, yeah, we discovered backpropagation, we're going to solve everything. Well, but now your computer is so small, you can train a neural net with 14 neurons. It's not going to do much. No matter how good your machine learning algorithm is, no matter how smart the people who set it up, it's just not going to solve the problem. Success is not possible. And now, when computers are operating fast, now we have a GPU, the new NVIDIA GPU can do 100 teraflop. Can you believe that? One GPU, 100 teraflop, that's pretty good. And now you can train big neural networks, and they can do more. And the reason that I feel a lot of excitement about the future is that even though Moore's law is dead, our laptops aren't getting much faster. Neural networks hardware is very much alive, and progress there is very rapid and exciting. And I expect that in the next few years, we will see some truly unimaginably fast computers, which will in turn will allow to unimaginably to very exciting progress. So let's see, I have 2 more minutes. So I think in short, a lot of things are possible. The reason neural networks work are, A, because they're circuits, and finding the best circuit is a pretty good thing to do. And furthermore, we can look at human beings and look at a task they can solve in a fraction of a second, and from that make inferences about the kind of tasks big neural networks will be able to solve. Compute is really what's driving the whole thing, and more compute will result in better and more amazing applications. The one thing which I think I agree with some of the things that people raised is that the hypothesis class of neural nets, if you think about it as just a raw circuit, it's not the final hypothesis class. The final hypothesis class is programs. If you could find the best program, then you're truly done. We cannot find the best programs yet, but hopefully we could maybe wrangle these models a little bit so that the results, so that the things that we'll produce will be a lot like a computer program in one way or another. So yeah, that's all I have to say. Thank you very much.
So it's always difficult to go the last, since my colleagues have already said basically almost everything I wanted to say. But I will try my best to keep you entertained before the break. So I just wanted to start by maybe reiterating into, we are talking about the breakthrough of neural nets, and it's actually quite interesting because, we are not really talking about a technical breakthrough here, right? It's not that suddenly we have amazing new algorithms that, we didn't have before. Right, there has been a few, algorithmic tricks that, have helped into making this, making training, better. But there is no fundamental change in the last, 25 years or more. So why are we, why are we here? Why are we talking about breakthrough of, I guess, deep learning, or now rebranded as AI, right? To the despair of people like Stuart. So, what came together was these algorithmic tricks, the availability of a lot of training data that was labeled, right, like ImageNet, for example, that Feifei developed. And as Ilya said, better hardware, right, that was actually making possible to actually train these models at a larger scale. And something that we shouldn't forget is actually also, the hard work of the grad students, right, like Alex and Ilya, right, that shown, really impressive results in computer vision, and then the field turned after that, right? So it's quite impressive that, that they were able to convince the whole community that we should pay attention to these models. So why are we talking about breakthroughs? I think that the real reason is that these systems have enabled applications in domains that before we didn't think about as places where machine learning will make an impact, right? Whether it's health, whether it's transportation, whether it's the most boring application you can think of, you see machine learning, AI, deep learning almost everywhere, and it's interesting. And as Mike was saying, sometimes you can build a model that can fake things, that is very good at faking, and actually is okay if you don't rank your pages exactly the perfect way, but you can get away with doing a lot of things this way. Now I work in self-driving cars. This is a critical safety application, right? So you can't fake things, right? You actually have to make sure that the system is robust and is not going to make wrong decisions. And this is actually quite challenging for neural nets. For example, one of the issues is that they don't really model uncertainty well, right? So they will tell you, there is a car there, for example, with 99% probability, and they will tell you the same whether they're wrong or not, right? Most of the time, they're right? But when they are wrong, actually, this is a really real issue for, in this case, for example, self-driving. Right, so you can't build a system that has false positives, and you're going to start just braking in the highway at 120 kilometers per hour, whatever number of miles that is. So that's an issue that I think we should think about, and this also links to a better theoretical understanding of neural nets. Right, so can we have confidence intervals of the error they're going to be making, and can we build systems that again they are robust based on this? I think that another thing that is interesting that hasn't been brought up by my colleagues is whether now that we see a plethora of applications of, say, deep learning, is whether legislation is going to catch up with progress of technology, right? So, and self-driving cars is one of the examples of, are we ready to deploy these things? And will we be ready? And what do we have to change in order for that to benefit each one of us? So I think it's something that we usually in an academic environment, we don't think about it, but I think it's, we are at the point where we have made so much, our technology has made so much impact in industry that we really need to think about that. Other things that I think are important, and Stuart mentioned this, is the fact that, with neural nets or traditional neural nets, we're forgetting about modeling. We're forgetting about prior knowledge. We're forgetting about, how can we encode the world in a way that actually is more interpretable? And, again, we are able to get, confidence estimates about what we see. And perception is one of the, canonical examples of this, where there is a lot of room to actually incorporate prior knowledge, incorporate, good modeling, and at the same time learn these representations because we don't have good abstractions of pixels, for example. Right, so looking at things like graphical models and neural nets and how these things can tie together, I think is a very, very interesting direction for the community. Something I also wanted to bring up is the fact that as there is more and more people actually using deep learning, we should think about education, right? We should think about, are people aware on the underpinnings of the technology they are using, right? So one canonical example is fairness, right? So when people use, our models on the cloud or whatever to, with their own data to train systems, do they understand that the systems can actually have biases? And as we deploy this in applications that matter for our everyday lives, are they understanding that perhaps they're going to make decisions that are not fair, that are going to, impact certain sectors of the population, perhaps not in the right way? So I think that's something that, as educators, we should be really thinking about, how we make sure that people understand what these models can do, cannot do, and what potential caveats of the models are. And I just wanted to, finish with a positive thought, right? I said a lot of negative things, which is, where, for me, the future of deep learning, I think, I want to just talk about a little bit on applications and, self-driving cars being just one really, really exciting area. But transportation is just the first thing, towards really getting smarter cities, right? Our cities are growing, they're getting much bigger, and there is, a lot of issues that come with this, and I think that machine learning can really help for us to have a much better life. And when we think about this, right, so self-driving cars, for example, can, can save lives. There is, I think it's 1.2 million deaths per year in the roads in the world, right? That's a tremendously high number. We can reduce congestion, pollution. Studies says that there is only 1/10 of the cars that will be needed, right? But we also need to think about that it's not about building technology. We should also think about is the way we use the technology, right? If each one of us is going to just use a self-driving car individually, we are not going to help our planet, right? This is not the way to go. We should think of, public transportation, car sharing, ride sharing, and the same. And it's not just about transportation, right? It's about everything that we have, right? Our planet has limited resources, and we should think about how new technology can help us to make the world a place where everybody is equal. Thanks.
So I'll start our discussion by trying to summarize what I got from the panel so far. I'm glad to see that the people who are deeply involved in deep learning are aware of the limitations of these techniques, and they characterize it as it's a tool. It's a tool. It's not AI, not a human-level AI. It is a tool to be used in the context of other tools. But as a part-time theoretician, I would like to ask for a more clearer definition of the boundaries. If you are aware, if you can tell us more about the definition of the boundaries of capabilities of machine learning. Am I right in assuming that the boundary that I outline here, namely going from distribution to interventional questions, going to counterfactual, is that the boundary that you are worried about? Or is there something more than that? In my simple-minded mind, I view machine learning as a tool to get me from samples to distribution.
So
and then we still have two more steps to go from joint distribution function, right, into real intelligence. Two big steps. One is experimentation, and the third one is counterfactual. Am I right in segmenting the world that way? Or it has nothing to do with the thing that you are worried about? That is my question.
So I think the whole big problem is decision-making under uncertainty. And finding a mapping from A to B is just one little part of that. So, yes, you have to worry about counterfactuals and what might be. You have to think about rollouts of what's not really working and what might be working. There's a whole system you have to build when you think about it. You have to think about the economic issues. So, it's kind of things I find exciting with all the data around we can create new markets to link producers and consumers. So one I'm kind of involved right now is music, that there's tons of people who love to listen to music and tons of people who like to make it, and no one's making money off of it. Well, there's all this data. We can bring them together and let each musician know who likes them and create all these things. So that's a huge computation meets data analysis, meets prediction, and then many decisions being made in parallel. And then whenever you're making decisions, you have to think about the causal side. Because if you wiggle something and it doesn't give an effect, you can't actually do an action. You can't have control over the environment. So why would everyone separate out? The learning part is over here, and there's a boundary around that, and the decision part's over here, and the counterfactuals is over here, and the Monte Carlo testing out multiple alternatives is over here. It's all part of an integrated systems way of thinking.
And I also want to just point out, one of the fascination to me, but challenges of working in AI is actually we as a civilization has very little understanding of cognition and like what human cognition is. And that's actually a really important sister field of AI. And because of that, we are, in a way, we're inspiring each other and learning from each other, but both at the very beginning. So when you talk about the boundaries, we don't even know the clear definition of what human cognition is, human intelligence.
But it's much easier to build boundaries on artifacts, like deep learning. That's an artifact, or a neural net. That's something that we have created so we can analyze it and come out with the boundaries. Are we there?
Maybe one remark to make is that neural nets use backpropagation, which is the chain rule of calculus, to go back and change all the parameters everywhere. That's non-modular. So it's an end-to-end kind of way of thinking. You get an error out here in some part of the system, and you percolate everything back and make little changes everywhere. That's kind of antithetical to computer science modularity and keeping things separate. So that's just a fact we have to face, is that these systems that give the highest performance are going to make a system that's not very modular, not easy to understand, and not very easy to diagnose with. And that doesn't mean that one's right or one's wrong. It's just that we're going to have to face that issue going forward. That performance and explainability are a bit in trade-off. And also just thinking how humans think about the world, we don't really separate off one part from the other. Things over here can influence other things over here, and we're kind of happy with that. And so the keeping things simple in modules is something that we may have to sort of slowly release as part of systems that really learn from data and take into account all the possibilities out there.
So I have two things to say. First is about modularity, and second is about how to think about the limits and the progress in the field. I actually like the comment about modularity. I think there is a bit of a nuance there that the end systems that we learn usually tend to not be particularly modular. But now we have the ability to, we have these great blocks which we can compose together to create whatever neural net we want. Then we train it. And so it's really convenient that you can take any kind of data format that you want on the input side and almost any data format on the output side and set it all up, and the system is going to work. And what's interesting is that all these different applications, they're all driven by the same set of algorithmic constructs, by the same set of ideas. And what that means is that anytime anyone makes an advance, the advance goes at the level of the, often can go at the level of the algorithm, that will expand the boundary of what is possible, not just in one application, but in all applications in general. And so it is true that some kind of boundaries exist right now. They are a little bit blurry, and they're still being pushed. And I think it's hard to tell how far we'll go just with the current set of ideas, excluding any new ones.
So I think it's instructive to look at AlphaGo. So everyone's very impressed by the fact that AlphaGo is now wiping the floor with every single human being on Earth. And it's often described as a deep learning system, but actually it isn't. It's a very classical system. It would be easily understandable by Arthur Samuel. It's essentially an improvement on Arthur Samuel's system from 1957. And it has several components, and the deep learned part of it is just one, well, I guess it's two of the components, but perhaps the core component still is the fact that AlphaGo knows the rules of Go, in the sense that for any given position, it knows what the legal moves are, and it knows what the next state will be when each of those legal moves is executed. So that's the causal theory, coming back to Judea's point, the causal theory of the domain, and that's written by hand in C++, or something related to C++, right? It's not learned. The learning part of it probably wouldn't work. It includes transitive closure because the liveness of a Go piece depends on its connectivity to all other Go pieces, and so there's a transitive closure thing, which is hard to do in a fixed depth circuit. So potentially you could learn the rules, again, by experimentation, but in fact they found it much easier to use a nice expressive programming language to write those rules, because as we know, the rules of Go are pretty much translation invariant across the board, and they're also time invariant. And so there's that. And then there's the forward search, the exploration of future possibilities, which again is a very classical idea going back at least to Aristotle and maybe earlier. And so this I think is emblematic of what we're going to see going forward, that the way we build systems is not just end-to-end. If you took seriously the idea of end-to-end deep learning of Go, you would have to learn a policy. Namely, you would take millions and millions of Go boards, you would take the move that was made by some expert program or by human Go masters, and you would train a policy that maps from boards to moves. But that is not how it works. That does not, as far as we know yet, work very well. People have tried that approach in backgammon, for example. It didn't work very well. It doesn't work for chess at all. And so it's this breakdown of the decision problem into its underlying elements, the transition model for the domain, the ability to look forward in time, and the modular knowledge of how to represent the transition model and what it does. Those elements, I think, are crucial, and they're not end-to-end learning.
Related to that, and what I was trying to introduce here, can AlphaGo take advice from a human being? You shouldn't have done that. You would have been better off had you taken this move. Would it be able to understand this kind of advice? Or perhaps it needs a whole new architecture to be able to understand such advice? That's my question.
But it's not an architecture, it's a problem to be solved. So if you sat down and wrote AlphaGo as a program, as Stuart's talking about, you do a lot of Monte Carlo rollouts, you build a policy up, and you build a system that does that. Right now, that's reinforcement learning is the underlying technology that does this. And it's a kind of dumb try things out, but then kind of smart engineering to make it not intractable. There's something called apprentice learning in reinforcement learning. It's another part of reinforcement learning where you take advice from a human. You watch a human doing it, and then you learn that. So it's all a big toolbox. It's not that you're building an architecture that can or can't do something. It's that you sit down as an engineer and you say, I want to make a helicopter fly, or I want to do a Go. And we're not building a single device that does all those things. That maybe in 500 years we'll do that. But right now what we got to develop is an engineering side of our discipline that thinks about how to build a system that does, here's the goals of the system, here's my guarantees, and here's how I build the system. And we're so far from that we have to get real. We have to think of systems way of thinking and machine learning. To me, there's a lot of systems people in the audience, and I think that your way of thinking together with the mathematics of machine learning, that's the future.
So I agree with Stuart and Mike of what they've been talking about. I think that we shouldn't just think of deep learning as it's going to solve all our problems and it's going to learn anything whatsoever, right? So I mean, it has very high capacity, but still you need to be able to get to that solution, right? So for example, one can do a demo that works pretty well into how you input images and then you output the steering wheel. And that's fine for doing a demo, but that's not going to solve the end task of it has to work at every point in time. And when you make a mistake, you need to explain why you made that mistake. And this is why then you need to, again, interact with modeling, but at the same time, when you learn your neural net components, they should be aware of the whole system. And that's the interesting, difficult part on all this.
Unless you have other comments to make, we are going to open the floor for questions from the audience. Oh, no questions. So, okay.
Wow.
Yeah. Education was mentioned. What should we be teaching or learning ourselves to make the most significant advancements? What are we, what is supposed to understand or teach? Any comments on that? I have a comment. What do you teach in a neural network kind of class? It's related to the question.
I'll just say one thing, and then Stuart, I just finished teaching the largest neural network class at Stanford, 770 students. We teach neural network. We teach calculus. We teach chain rule. We do Taylor expansion. We teach backpropagation. And then we...
what is not true about neural network?
What is what?
I'm saying not true because teaching is conveying information. Information is what cannot happen in the world. So tell me about neural network. What are we sure cannot happen in neural network? If I had another layer, it's not true that, go ahead.
So one thing about this kind of statement is that this statement, so a neural network is a circuit of a certain limited size. And that question is related to the question of what can a circuit of a certain size not do? And those of us who are more on the theory side know that these questions can be extremely difficult to answer. And this is precisely why it is so hard to delineate precise boundaries of what can and cannot be done. And there's a lot of experimentation going on. And oftentimes, you think that something can be done, and then later someone figures out that it can be done.
Yeah, so I'm rewriting the AI textbook right now to figure out, how do we incorporate deep learning. And we have a real problem because we have a vision chapter right now, and then Ian Goodfellow is writing the deep learning chapter, and I suspect the vision chapter is just going to say, see chapter 19. Right? And then we have a section on speech recognition. It's going to say, see chapter 19. So this worries me because then you don't really understand speech. If your approach to speech is get lots of speech data and train a deep learning system, and your approach to vision is get lots of vision data and train a deep learning system, I think that's really selling the student short on understanding the speech problem, how it connects with language, how speech is produced, the structure of sound, and then the same with vision. So I think we're really struggling to figure out how to retain the core content of these areas, even though the fact is that right now, by far the best speech recognition systems are end-to-end deep learning with really no internal structure. All the stuff that we used to teach about hidden Markov models and acoustic models and mixtures of Gaussians and all that stuff has gone by the wayside in practice. So that's a problem.
I hope you have a good chapter writer for vision, because I think that's exactly what we do in the labs. We talk about what we cannot do in vision, right? Like the whole 3D vision understanding. Even in object, there is, because of ImageNet, a lot of people think we've solved vision. It's not true at all. We all know what are the open problems of vision. We don't understand we don't even understand objects themselves, the parts, the relationships, the affordances, how it can be manipulated, the texture, the transformation under all kind of variances. So I think this is so important in the days of deep learning, especially in the hype days of deep learning. We actually have that discussion and analysis.
Good. Are you volunteering to Thank you.
So can I make one more brief comment on, I just take an opportunity to say something about the curriculum in general, not just deep learning, but the CS curriculum I think needs to be revisited to have more statistical, and so I like to call it inferential thinking. The counterbalance to computational thinking is inferential thinking. If you're doing an A/B test in industry, which people do all the time, you're trying to think about what could happen next, what's behind the data. That's a form of inferential thinking. Error bars and confidence intervals are things that could happen but didn't happen, but you have to protect yourself for. And too few of our computer science ever see those concepts. So one way of doing what she's talking about is the cloud. You do things not just once, but you do it in parallel 100 times, and you can get an error bar. So there's a natural match to some of the ways we think in computer science to the needs of inferential thinking. And I think our CS curriculum just needs to be really revised from the bottom up to start introducing those concepts. You can go through a whole CS curriculum and see a little probability, but see really no inference. And I think that's really something we have to change. And that's what I teach when I teach things like neural nets. I say it's part of a bigger picture of statistical decision making and inference.
Yes, I think, just one more comment. I think it's very important that a neural net class should start by what is machine learning and what are neural nets in the context of machine learning. By making sure that everybody has a bigger perspective and it's not just deep learning, which is unfortunately what is happening in many, many places that they just forgot about the rest.
I want to apologize for my biased selection of the questions, which are affected by the legibility of the handwriting. Here is one that I could read. How and why should people trust a deeply learned system that makes a decision? How can they expect why should we trust recommendation made by deep learning system.
So that allows me to bring in another theme that I like to make, which is databases. So we can't divorce this style of machine learning thinking from database thinking. Database people, for example, talk about provenance of data. And I need to be able to track back where a data point came from before I'll trust an inference made by a box that was trained on that data. So in medical decision making, you have all the time that data was collected in some era, a learning or statistical system was built based on that, and then 10 years later, the inference system is still being used, even though the machines may have changed. So the data is actually out of date. And if we don't build systems that take that kind of provenance into account, so that you can say, you can trust this inference, not just because it's a deep learning system or whatever, but because it came from this place, and that makes your inference relevant, then you're not building an overall system that you can actually trust at all.
So I think we should think about, humans are pretty, many times pretty bad at making decisions, and even worse at explaining why they made those decisions. So, we need to think about we are also extremely hard with machines, right? And we should keep them to the same standards.
And here's a question. Can you discuss the issue of mental modeling? I couldn't read the next. And if I ask, how do you fix a broken phone, you can answer it without breaking your phone. And anyone wants to comment on that? I mentioned that ability to be able to have a mental representation of the environment, and one of the greatest breakthrough in the computational capacity of Homo sapiens. So yes, if you have a causal representation of your environment, you should be able to manipulate it in your head before you do it physically. That is the great advantage of having a mental representation, and this is one element which I do not find in neural nets. So evidently that is something to work on. Another one is how, yeah, here. Oh, there's one question here about the specialization of neural net. What we find today is machine learning today, the systems we find today are specialized. Do you think that pursuing a general purpose machine learning AI is really worth it? Unless you...
So I can say a few words on that.
I would say, is it feasible?
So special purpose versus more general purpose, it really depends on the problems that we're trying to solve. Many problems that we're trying to solve are indeed fairly specialized, and so for those problems we should use the most specialized approach possible. But as we set our sights towards more ambitious goals and more ambitious systems that can, let's say if you think of, let's think of an automated mathematician. I think a system like this will need to be quite a bit more general than a system which does something quite narrow. And so what will happen is that it's not quite feasible today, but as our computers will inevitably get much faster, I think these kind of systems will become, at least it will become possible to design systems which could credibly, you could imagine, if you just give it the right experiences, would do what you'd want.
Anyone else on the question of generalizability?
I think the way to approach it is to always play devil's advocate with yourself and say, okay, I built something that I think is more general than something else. Where does it break? So if you take, for example, DeepMind's DQN system, which is somewhat general, it learns to play a wide range of video games purely from the visual input provided by the game. And that's held up as one of the first examples of something that moves towards general purpose AI. And it's driving games, it's ping pong games, it's mazes, and all of it. If your baby learned to play those games at a superhuman level in 2 hours after birth, you'd be pretty terrified. But when you actually say, okay, well, does that technique generalize? Well, the number of time steps that the system is capable of handling in terms of the timescales of rewards, the timescales of realizing the benefits of actions and so on. It's in a few tens. When you think about, okay, now translate that to human physical action and the scales that we operate on, which can be deciding to go to a conference months in advance. The conference itself is hundreds of millions of physical actions. And we make decisions on the scale of billions or even trillions of physical actions. It doesn't possibly scale up to that. The approach does not work, it fails, it breaks. And then you have to say, okay, what could we do to get past that bottleneck? But there's not an infinite number of such bottlenecks. And we will pass through them eventually.
Thank you, Stuart, and thank you, all members of the panel, and thank you for the audience for being so patient with us, and thanks for the opportunity to present these ideas.
So let's round of applause for the panel.